MoneroKon 5 in Prague at Second Culture, formerly known as Parallelnipolis. Our next speaker is well-known technically and socially in the community. He's recently sort of like switched camps and is wearing another chain's branding. I highly suggest that you look at the work that Alpin is doing. They're on the front edge, and Aaron's going to be speaking about something totally different today. Pleasure to welcome you again.
Thank you. All right.
Aaron Feickert.
All right, sweet. Thank you very much, and thank you for coming to my talk. So I'm Aaron, done research also as Sarang on the Monero ecosystem, and today I'm going to be talking to you very briefly about how exactly in different cryptographic protocols that do effectively transactions, how we actually prove coin ownership, which is a very important part of ensuring that a blockchain ecosystem works the way we expect it to. So I'm the research engineering lead at Alpin Labs right now. Indicated by my shirt. And we do some very fun cryptographic plumbing that I'd be happy to talk to you about later, but I'm not going to talk about that today. So the question we want to answer is how exactly do we spend coins in a cryptographic way? So what we need to do to effect a transaction protocol are more or less four different things. If I want to spend a coin to you, first I need to prove that I actually own or control the coin to be spent, that it had been previously spent to me either through a mining process or through another transaction. And this is the important part that we're going to be talking about today. Kind of secondarily, we also, but importantly, need to assert that that coin has not already been spent. Otherwise, tragedy ensues. This is effectively the double spend protection that you often hear about. Third, of course, I need to indicate who or what is the intended recipient in a cryptographic way. And then, of course, we need to ensure that the transactions actually balance and that no coins are created or destroyed. It's like energy. But the way that this is all done depends very, very heavily on what protocol/asset you use, whether or not it's Monero or Bitcoin or Zcash or whatever. These are all very different, but effectively they need to do the same thing, which is these four things. But we'll be talking about that first one, which I think is in some ways the hardest one, which is how we actually prove ownership, and how we prove ownership in a safe way. Of course, like the earliest example, the first one that kind of started this whole thing was Bitcoin. Bitcoin does it in a very, very straightforward way that has a lot of safety implications. So what that does in a transaction is we take some input coin, we have some authorization for it, and then we have some kind of output coins. So the transaction directly identifies what coin we're spending. This is very straightforward cryptographically. You just say it in the transaction effectively. And what the output coin is and where it's going. And that can differ a little bit. And then we assert spending authority using a form of a digital signature. Early digital signatures were actually quite bad, ECDSA, they've gotten better, but it's a pretty straightforward process. But we can do a lot better than that. So because of the simplicity of this little very vague diagram that I drew, I can just look at the chain and I can know the spend status. So if I look at any coin, I can tell you if it's been spent or not by just looking for a transaction that may spend it. I know the value because it's specified in the transaction, and I know its trajectory. That is, I know where it goes and I could just follow it through the chain over time. So if I know that, of course, so does every company that wants to do chain surveillance, every criminal who's even remotely savvy, and every adversarial government. So we can do better than this. But how do we do this better? So we're going to look at kind of three broad approaches. I'll say from the start, these are not the only three approaches, nor are these the only three protocols that use these different approaches. But I'm going to kind of take these as kind of prototypical examples. We'll look at three different constructions and then three corresponding protocols/assets that end up using or that will use these approaches. The first one is going to be CL-SAG, which is the technique we use for asserting coin ownership in Monero. The second one is a technique that I'll just kind of call Groth boodle proofs. I will not actually be doing any math in this, don't worry, but we need a name for them. These are used kind of prototypically in Firo, in its Sigma and Spark protocols, and it was actually proposed as well for Monero Seraphis, which is kind of a predecessor to some new protocols that'll be coming out. So to my knowledge, Seraphis isn't really being used anywhere, but it's cool that it can be used in both. And then finally, we'll talk about some Merkle proofs, which are used kind of in Zcash. I do say Zcash, not what I will call Tcash, its transparent equivalent, and also proposed to be used in Monero's FCMP++ protocol, which I know you'll probably hear a lot about today and has been talked about in the past too. Each of these does have different trade-offs, and we'll very briefly go over what those are. So there's kind of like a dirty little secret to all these things, is that they basically all need to do the exact same thing. They need to assert coin ownership in a private and safe way. The way that they do this in each of the cases is different. The trade-offs are different, and like the underlying mathematics and plumbing are different. So I'll say the fundamental difference between these is not something like, do they use snarks? Do they use signatures? Is there some kind of encryption involved? Those can be important, like, don't get me wrong. And again, they do have implications on how they're used in the different protocols. But really, it's about like the size of the possible spending set when, in which we're proving coin ownership and what method cryptographically, mathematically, we're using. So in all of the cases, what we want to do is secretly assert that a spent coin in a transaction is controlled by me, and that it's contained in some set of possible existing coins that we specify. So like I said, the difference is like the size of what that set is and the plumbing that we use to make this assertion of ownership. The first example we use is what's used in Monero currently. It's called CLSAG. It's a linkable ring signature. So linkable ring signatures are a type of cryptographic primitive that basically assert that I know the opening to like one of several cryptographic commitments, and that I have some kind of linking tag associated to it that I can use for double spend protection purposes. It kind of like binds those together into the same construction. Monero's used several different versions of this over the years. It used to use one called MLSAG. CLSAG does the same thing, but in a more compact way. So I'm not going to go through like the mathematics behind this, because I don't think it'd be terribly insightful unless you already know what it is. So instead, I will use a vague diagram, which is much clearer. See how vague it is up there? It took a long time to do that. I'm not an artist. So when we call this like a ring signature, the term ring is kind of used interchangeably, depending on who you ask, to mean one of two things. Some folks use the term ring to refer to like the set of possible coins itself. Okay, fine. Realistically, like what it means, why we call it a ring, is that the construction that we use to generate and verify the signature has kind of a ring-like structure. We want to kind of complete the ring. So what we end up doing is, suppose that I have a set of possible coins, and now in Monero, we basically take these from a particular distribution that varies in time, and there's a bunch that actually goes into how we pick this set. But we have to pick a fairly small set of possible coins for which I want to assert ownership of one. So suppose that I have these 3 coins, and maybe there's some more along the way that I didn't draw here. And let's suppose that I know the opening, the secret, the key behind one of them. We'll say this one here. So what I do is I kind of go through and I kind of have to touch each of these coins in order. And what I do is I take each of them, I put a little bit of information about the coin into a cryptographic hash function. And I get some output there. Hash function takes input data, does kind of a mangling in some sense, spits out some more data. Switch, I use this hand. So we take that first coin's data, run it through a hash function, we get something out. Then I take some data about the second coin and that data that I got out about the first one, run that through a hash function again, and keep going. But when I get to the coin that I control, I embed some information about the key into that data, and then I keep on going. And at the end of the day, I don't just have like this line of different hash functions involving every coin in the possible set. I'm able to like loop this back around again to the first one. And if you actually sit down and look at the math, you'll see there's kind of this looping ring-like structure. And the key is, when I do this to generate the signature, and I get some data out that I'm able to post on chain, when anyone needs to verify the signature, they also touch each coin in the possible set. And they do kind of a similar version of what I did to generate it, except they don't know what the key is. And the trick behind this, and what makes it cool, is that the verifier who's verifying the signature is only able to complete this process, in line of complete the ring, if I knew the key to one of these. If you don't know the key, you're not actually able to complete this ring-like structure involving the hash functions. And then there's some stuff that goes in with linking tags and key images as well. But it's a really cool construction, very clever. There's a certain elegance to it, but it requires that we touch each of these coins mathematically. So this does have trade-offs, and a lot of research into like the Monero and related ecosystem is about these particular trade-offs. One benefit that these have is they are pretty straightforward to generate and verify. The math that actually goes into this diagram is not very complicated. Like, you can look at the code. It's surprisingly short for what it does. But the downside to it is that the size is linear in the number of coins. So that means if I have like 16 possible input coins that I'm asserting spend status for one of, the size is basically going to have like 16 of those, 16 elements to it. So we say that that's linear in the number of coins in the input set. So the scaling is pretty limiting. If I wanted to, say, have 1,000,000 coins in the possible spend set, that becomes very large, and we don't want to have to post all that data on chain. It would bloat transactions quite badly. And another reason we wouldn't want to do that is when we're verifying these signatures, which we need to do in consensus in order to actually go and process the blockchain. That verification process is also linear because we, the verifier, also need to touch every possible coin in that set. So again, if we had 1,000,000 of these to do, that would just grind the chain to a complete halt. So overall, the scaling is very limiting. And because we have to limit the size of the input set, that also allows for a lot of possible analysis, unless we choose those coins very, very carefully. A lot of work has gone into choosing those coins carefully, but there's a lot of subtlety to that. So that's one. The second one we'll look at is called Groth-Boodle proofs. These are used in different protocols. Some kind of well-known ones are Firo's Sigma and Spark protocols. I worked on Spark. And also the plan for Monero Seraphis, which, to my knowledge, has no plans to be deployed. They use a particular kind of one-of-many proof that asserts coin ownership within a particular set of coins. But typically, it's kind of a larger, bucket-like structure. And the reason I call it a bucket-like structure is that every time a transaction adds a new coin into the chain, into the set, we basically tack it onto that bucket and let that bucket grow over time until we hit some kind of practical cap. This works a little bit differently than kind of the CL-SAG type proofs. You will notice there is no ring-like looping structure here. Instead, what I do is I take my bucket of coins, line them all up, and kind of number them with an index. Typically, we can do this in binary or in another number system, which affects the scaling a little bit. And let's say that I know the key to the third coin here, because we always start in computer science counting at 0. That is the 0, 1, 2 indexed coin. So I know the key to coin indexed 2. I write out that index in binary. I just wrote out 4-bit representation of it there. And what I do is I do some math on this index and on the key. So what I end up doing is I do have to go through and touch every coin, but I only have to operate using the particular index that I know. There's actually this kind of tree-like structure that goes on underneath this with the math that you don't really have to know much about. But the idea is that instead of doing this repeated hash operation like I do in CL-SAG, I just take the index for the coin that I know, I take the key for the coin that I know, I touch every coin and do a little bit of math on it, and I end up with this one-of-many proof structure that a verifier can verify in order to assert that I know the key to one of these coins without actually revealing which index I know. So, as always, there are trade-offs to this. Similar to CL-SAG, the proofs are fairly straightforward to generate and to verify, although there's some caveats. It's a little bit more complex, but not overly so. One of the main benefits to this is, remember, CL-SAG signatures were linear in the size of the input set. So I basically needed some element in the proof that I put on chain representing every possible coin in the input set. That is not the case here. Here, it's actually logarithmic in the number of coins in the input set, which means it scales very, very well. I can keep on adding more and more coins to this bucket, and as I do this, the proof size effectively gets almost no bigger. It gets a little bigger, but not too much. Unfortunately, verifying, which again we need to do in consensus to process new transactions and ensure that they can be properly added to the chain, that unfortunately is linear, because we do still need, when we're verifying, to touch every single coin, do a little math on it to do this verification. So there's kind of a disconnect here. The size that goes on chain, that's logarithmic. The verification process is effectively linear because you have to touch every coin in the bucket. It is possible to use the fact that we have this bucket structure where I'm adding coins iteratively every time there's a new transaction. I can use that to my advantage in order to do what's called batching and verification, where I can take a bunch of these proofs, kind of stick them all together in a pot, do some math just on that pot, and then get the result for all of them. It is possible to do this, but you have to be careful. There are some subtleties. We go on. So the scaling is better, but it's still fairly limiting. So for example, maybe instead of having 16 coins in a possible input set, you can go, depending on the volume of your chain, into the thousands perhaps. But no, not too much larger than that because of this linear verification process. Finally, let's look at what is probably more or less the state of the art at this point, which are Merkle proofs. So these are used in the shielded Zcash protocols, but not its transparent variant, and also will be used in Monero's upcoming FCMP++ protocol. They use what's called Merkle proofs. And what they do is they don't assert coin ownership within a small little specified set of coins or even within kind of a growing bucketed set. Instead, they use a so-called Merkle tree structure. And the idea behind this is, let's say that I have in this case, what I have 8 coins there, I'm going to form kind of a tree structure with them to get like a representation of all of those coins without having to like write them all out. So what I do is I take some information about each coin, and there's a lot that goes into this that I'm not going to detail. And for every pair of these coins, I basically apply a hash function to both of them, and I get some other value out. Take those two, hash, get a value, hash, get a value out. And then I iteratively keep on going at each layer of this tree. Now I take these 2 hash values that I got out, I hash those together, get a new value. Take those 2, hash them, get a new value, until finally I end up with, at the very top, I get one final value out. And that's called the root of the tree. I don't know why this tree is upside down. Computer science is weird. The root of the tree is at the top. This is why a lot of people don't like math, I guess. I don't know. But anyway, this tree root is some kind of very safe cryptographic representation that somehow encodes information about all the initial coins that I started with. And the reason that this is really cool, one reason, they're cool for many reasons, is let's suppose that I know the key, the secret corresponding to this coin right here. If I want to prove that that coin is contained inside this tree structure, given only initially this root that somehow represents all those coins, but we can't use that root and like undo the hashing. We can't like get the coins back from that. But what I can do is I can basically provide all of the sibling values to nodes in this tree and allow a verifier to reconstruct the root. So if I give you this coin that I know the input key to, if I give you its sibling node, you can construct this hash. But instead of giving you all the other coins, I will instead take this hash. I'll just give you the other hash here, and then you can compute this value. Once you have this hash over here, I don't have to give you all the stuff on the right. I can just give you this orange hash over here, and you can use that to reform that tree. So if you sit in like a dark room with your favorite beverage and think about this for a bit, you can convince yourself that instead of having to give you all the information about all of these coins, I only have to give you a few select values, the orange values, and you can use those to reconstruct that same tree root. And if you do that, you can be assured cryptographically that in fact, I did know information about one of these coins. Now, this, what I've described here, it doesn't actually hide which key we're using. Like there's more that goes into this. But the trick is that because I'm doing this, I only have to provide you with a small amount of information as opposed to the information about all the possible coins and what could be a very large tree representation. So more or less, this is how a tree structure kind of works. So there are trade-offs to this. Like I said, we do have to, there's more math involved to like actually make this zero knowledge, which means we hide the, where the actual coin is in the tree, because I don't want to reveal that. But the requirement for having this be zero knowledge does make the proofs more complex, and particularly to generate. This was like kind of an initial limitation to early versions of this, like particularly like the early Zcash days. These problems for generation have mostly gone away, but there is still more complexity than in, say, Groth Boodle or in something like CLSAG. We do also need to update the tree. In the case of the bucketed approach, it's very straightforward to add new coins to the bucket. You just kind of stick them on the end of a list somewhere. But for this tree structure, there was all this hashing that was involved, and we need to update the tree every time a new coin is added into the set, which happens with every transaction or block. That's a non-trivial approach, and a lot of work actually goes in on how to do that efficiently. A huge benefit is that the proof size, it actually can be as low as a constant. This typically requires like a trusted setup that we don't like, so in practice, we get like logarithmic size complexity, which like Groth Boodle means that I can increase the number of coins in this tree representation immensely. And the proof size gets only very, very, very slightly larger. And in practice, like we just know what that size is, and so we're okay with it. And verification can also be as low as constant if we have a trusted setup, but in practice, we can actually also make it logarithmic, because remember, in this tree structure, we're not dealing with all of these values. We're only dealing with certain values to reconstruct this tree root. So the scaling basically means that you can get effectively unlimited set sizes. You do need limits in practice, but realistically, like they're so large that they don't matter. And that's fantastic. The larger that this input set size goes, the harder it is to do like surveillance type analysis and have other safety concerns. So it mitigates a lot of those. So in FCMP++, let's talk about that just briefly. So that's a proposed Monero protocol upgrade. It stands for full chain membership proofs that realistically like implement these Merkle proofs. And I'd let the input set sizes be realistically the entire chain. Notably, this is actually different in Monero than in other designs. So the plumbing that's actually used for ownership assertion here, Under the hood, it's called a curved trees proof, and there's some other associated stuff. I won't go into the details, but I can discuss it later with you if you want. Great benefits that you get for the Monero protocol. It maximizes like the spent coin set, which is great to mitigate safety concerns. We talked about it as really, really good scaling. It's a very modular design, and it's very flexible to other aspects of the protocol, so it plays nicely with the existing Monero protocols. And I also think that there's a benefit to it in that it avoids a cryptographic monoculture. By that I mean if everyone were using the exact same cryptographic plumbing across the ecosystem, that does have benefits, and that a lot of eyes can be on the same cryptography and we can analyze it. But I argue that there's also some risk, in the event that something breaks or in the event that we want to, play differently with different trade-offs. So I think there's like a subtle benefit to that. So how does it differ? In things like, for example, Zcash and related protocols, they typically use like a very general purpose, what's called a circuit proving system, to do those Merkle proofs under the hood. And they also use it for other aspects of the transaction protocol as well. In FCMP++ for Monero, it uses what's called a bulletproofs-based circuit proving system a little bit differently. So it's not just kind of a one-to-one correlation between, use bulletproofs as your proving system versus another circuit-based general proving system. There's some differences under the hood as well. So it's not quite the same, but at the end of the day, it's doing a similar thing, a Merkle proof. So overall, very vague chart here. For the initial CL-SAG design, we had size that was linear as well as verification and a small set size, so not ideal. With Groth-Boodle proofs, we're able to improve the size. The verification is still linear-ish, but at the end of the day, it means you can get maybe like a medium set size. If you have Merkle proofs that use a trusted setup, you can typically get constant size and verification, which is pretty great, but you need a trusted setup. And the set limit there is large. It's effectively infinite. And in like non-trusted Merkle proofs that are typically executed today and will be used in FCMP++, you still get that logarithmic size as you do for Groth-Boodle. You also get kind of a logarithmic verification, which is also great, and still the same effectively infinite set size. So hopefully that's kind of a very broad overview of the fact that even though we have different protocols that have like very different approaches to asserting coin ownership, at the end of the day, they're all trying to roughly do the same thing. But as you can see here, with very, very different trade-offs. So happy to answer any questions on this if we have time, or discuss any of the details on this afterwards. But thank you.
Thank you so much, Aaron. One of the things that I enjoy about your talks is, I'm famously not a programmer and coder, but the language that you use to explain these high-level concepts that cryptographers work with is really fabulous. This guy is an amazing educator, really. Another round.
Nobody wants to see me do math on Zcash.
Cool. So we have 4 minutes, and I know that you can go into a lot of depth. Do we have one question for Aaron out of the audience? Otherwise, it'd probably be best to, okay, cool. Is that who I think it is? No? Okay. Similar hair. But here we go.
How do these complexities change in quantum computing situations?
Oh boy. We have 4 minutes, you say. I mean, you 40 minutes, you say. The answer,
TLDR.
Yeah, the answer is it really does vary. And so, I mean, at some level, all of these systems are broken in the context of like a post-quantum adversary. That assumes you can break discrete log problems. It means that you can recover private keys. It really depends on how they are integrated into broader transaction protocols. For example, Groth-Boodle proofs, the way that they're currently implemented, are definitely broken in that sense. CL-SAG is definitely broken. Aspects of the Merkle proofs as they apply to the full transaction protocol can be broken in very specific ways. We should chat about this later. I don't want to waste a lot of time on it, but the individual constructions themselves may not entirely be broken, but the way that they're integrated into the broader transaction protocol means that you could argue that they are broken. It depends. We should talk about it later. But it's a really good point, though. It's like these are just like one part of a broader transaction protocol that also involves addressing and balance assertions and things like that. And yeah, there's actually been some interesting analysis work in the past on like the Monero protocol's post-quantum resistance. And the answer is also, it depends on what component you're looking at and like what the consequences of that break would be.
Cool.
Talk about it.
Actually, we can do another question.
So in line with that quantum computing question, how real do you think is the risk of quantum computing actually breaking some of these protocols? Because based on what I know, quantum computing still may be 10, possibly many more years away because of a bunch of constraints like error checking. Error checking is still very difficult in quantum computing. So how realistic do you think is the quantum computing threat?
Oh, I have no idea. Depending on who you ask, it's either 5 minutes away or 500 years away, and I'm not qualified to answer that.
Kind of like
I don't
the
know.
coming of
Hopefully,
Christ,
hopefully
right?
hopefully far away. The reason I say hopefully far away is we do know ways to build certain cryptographic primitives that we believe to be post-quantum resistant, but they typically are either too inefficient. Well, it depends, right? It depends. That's my answer to everything. In certain contexts, the inefficiencies of certain post-quantum secure primitives might not be a big deal, for things like TLS or something on the internet. But typically when we're dealing with something like a blockchain-based protocol where you have to store data and transmit it and keep it often forever, that can become a big deal. The more inefficient you get, the bigger the deal is. They're always getting better, and we're building cooler primitives every day. But I don't know how far off it is, and I hope that it's far enough off that we can build more efficient primitives that are suitable for this use case. Right now, I don't think that they are at scale.
I'll give you a last question. Coding tools, AI-based coding tools are all the rage right now. What do you see? Do you use any of them in your own work? And where do you see that actually moving us forward using machine learning algorithms to advance cryptography as well, rather than just as a threat?
I mean, I don't use any to do coding day to day. I think I used an LLM one time because I couldn't figure out how to do a Rust thing involving references, and it told me. I don't know, is that AI coding? Maybe. Otherwise, no, I know a lot of people enjoy using them. I personally don't use them, but that's just me.
Purist. Aaron, thank you.
I'm not opposed to the idea of good tools. I don't know.
That puts us directly at 12 o'clock, and we got to
Nice.
move on. Thank you so much, Aaron.
Cool, thanks.